There we go. Yeah, when I first got out here, actually, one of the first things I did, which I really couldn't do in Manhattan, but up in Woodland Park, I'm actually up about almost exactly at 2,500 meters up in the atmosphere, which is somewhere between a quarter and a fourth of the way up in terms of molecules. But I got myself 3 digital thermometers, went outside, and some model planets, ping pong balls, and painted one of them black, as dark as I could, and one of them light, just as light as I could make it, to, if you will, test that old thing and also see, well, if these little bitty changes in our spectrum due to carbon are going to make these radical differences, well, then surely I should get a really big difference if I go all the way to black and all the way to white. And this one reads, one of these, I guess this one is off plus or minus 0.2 degrees. I don't remember. That one says 20.8. And this one here, the white one, just naked ping pong ball, says 20.9, but it's plus or minus 2 on this one. They agree. This one, interestingly, I decided to do a silver ball while I was at it. And you can see that that's about a degree colder. So there is a difference in what the surface makes. Okay, let's get some vocabulary. We've agreed everybody knows water is 273, melts at 273. And with a true zero, you can talk about ratios. That's why I can say it's 0.3% warming. All of this is so much above what an awful lot of the blog conversation is. And really, well, the thing that's generally talked about is watts per square meter, the energy impinging on the planet. And essentially, if you add it up, but I think that it's useful to understand that if you divide that, well, watts are joules per second, energy per second, so it's a flux. But if you go and divide that by a light second, then you get the energy density in a volume. That's a little bit of Einstein, really most fundamental Einstein there, that light and space and distance and time are convertible. And by color, I mean the full electromagnetic spectrum, not just visible, and so forth. And actually microns are put things in terms of wavelength. There are 3 modes of heat transfer, and we'll really only be talking about radiation. Conduction is pretty simple. It's second derivative Fourier, Pipples flatten is the way I put it. And convection is much more complex, but we don't need to deal with that because we're looking at long-term averages. So, so the climate goes and eddies around, or weather eddies around, but that's what matters first is going and calculating what the temperature is calculated by what the planet looks like from the outside, because that's what the sun sees. So Earth is a very colored ball in a vacuum, radiantly heated by a ball about 5,800 Kelvin, so far away that it covers only about 5.4 millionths of the celestial sphere around us. I mean, in some ways, it's that kind of surprised me, actually, when I calculated that the portion, I mean, that's all the way around 24 hours, all the way around the globe. The sun only is 5.4 millionths of that total sphere, the disk of the sun. Okay. And we really need, I'll throw in another law at the end, but we really need just 3 laws plus the geometry. And of course, the geometry is really to calculate the portion of the total sky that the sun covers, which ranges from about 5.23 millionths when it's furthest away at aphelion to about 5.6 when it's at perihelion. So the disk changes by about 7%. And you should be able to detect that if they, because the phase and the period and the magnitude. Should be able to pull that out of your noise. Okay, second, and here's sort of where you get Stefan Boltzmann, this is 19th century stuff. And as a matter of fact, it really is some of the most incredible accomplishments of 19th century physics. I'm blown away by 19th century physics. In any case, essentially, here's what it is. The power in watts per square meter, or whatever you want, power density, is proportional to the temperature raised to the fourth power. So if it's 288, you take that to the fourth, and that's what the corresponding energy flux is. When you combine Stefan Boltzmann with the inverse square law, which I think is the most intuitive law in all of physics, it ends up that the temperature decreases as a square root of the distance from the source. So here are for the four inner planets, Mercury and Earth and Mars. And you'll see, and this is the Stefan Boltzmann calculated temperature. And actually, as values, it's amazing actually how poor a lot of the, you'd think that the mean temperature of these planets is well determined. But even for Earth, they're not sure within more than a degree. But you can see everything sort of follows that law pretty closely, except Venus. Something's weird with Venus, and that's that's the climax of this talk. And just to go and recap, planetary temperature is linear with the temperature of the sun, and in our orbit a gray ball is about 1/21st, whatever the sun decides to be. Let me go back one. Okay, now we get to the one that will explain the balls. The tendency to absorb at a given wavelength is identical to the tendency to emit. Absorptivity equals emissivity for any wavelength. And here actually is one of those things. This goes back to 1833. This is just to restate the conversion of radiant energy to thermal energy in a material is it's like going through a filter the other direction. It's identical to the conversion of thermal to radiant energy. 1833, this guy Ritchie made this device, and this is actually from the early 1900s. This is the sort of device that they used to have in physics classes to go and teach this, and it's very clever the way it's made. Here it is sort of in more abstracted. I think actually this is from Richmeyer's book, the 1923 version, which I couldn't find. But here you have, and what's amazing is to use this, you just fill, well, these two chambers here are filled with water, okay? And they've got like a bubble or little some marble in the middle in here. And so they're filled so that these are, the marble's just sitting here in the middle. And then to do the experiment, you just fill this middle chamber with hot water, okay? So this is demonstrated with hot water. Here, this it says polished, but the thing that's incredibly clever about this is that through symmetry, it's gone, and so the hot water is emitting through the dark color here to a light color here, and on the other side, identically, it's emitting through well, this in this case, polished to black. And the thing is, you do that, and this does not move. The indicator does not move. It shows that again, that these two are just equivalent going in the other direction, so they exactly balance each other. And actually, it doesn't matter what colors you put there, it would work, as long as, and this is a rather interesting thing. Tyndall is one of these people who's often quoted by the warmists and so forth. But in his 1861 lecture, this is just very odd fluke that I happened to go and scan it, and right at the end he has, why should good conductors in general be bad radiators, and bad conductors good radiators? And actually, you think about it, aluminum foil, for instance, is really about the most reflective, bad radiator. Bad radiator. That's why when a lot of insulation batting, you have aluminum on the outside, because as a radiation barrier, but it is a good, by good conductor. It's a good conductor of heat, it's a good conductor of electricity. On the other hand, things that are bad conductors tend to be good radiators. We'll come back, but those two observations are something, again, we're talking stuff that somehow or other is not covered in high school classes or undergraduate classes even, or at least it's not paid attention to. Okay, with this 150-year-old observation, we can answer my question. And here, just a reminder, gray is constant. Absorption, emission, a flat spectrum, not just the visible. A gray ball, however, light or dark, comes to the same temperature. Okay? And, this is in the desert sun. Awesome. And finally, last rule we need to bring in is the power spectrum, the amount of power that a heated body puts out. And for a black body, absorption it's black. As totally absorptive equals 1, and emissive 2. So here, I won't go into it, but that's the entire. By the way, this is the total code to go and do these calculations also in APL. It's a function, essentially wavelength divided by wavelength times temperature over the exponential inverse. You can look at it. Anyway, this is what they come out. This is over a range from about 26 or 2.6 microns to, well, up bigger. But one of the things here now, this is the temperature of the sun, close to 5,800 degrees. You see, it goes up enormously, and here it is. And of course, its peak is way over here somewhere. We'll see, but this is sort of for the temperature of something in our orbit. Here, we've got scaled the sun by the 5 millionths of the sky that it is heating us with. And the red curve is created by going and searching for the temperature, which will have an equal area to this. So the energy coming in from the sun essentially equals the energy going out from the Earth. And they're off by a couple of percent, which just shows that even at this, granularity, I've not got the entire curves. And yeah, the total areas are given by the Stefan-Boltzmann law. Okay. And here I've just turned the sun spectrum on its side. Let's go back here. And one of the things is this is actually, I think, one of my, whether it's, I listed these numbers just to go and emphasize that these curves are just a whole set of numbers. I mean, I ran those, created those, the curves for all these wavelengths. Yeah, still says it's 60, but now it's Fahrenheit. Anyway, if I add up, here's the naked spectrum, and that's the same number that I got. I mean, that's just adding across. That's adding across each of those two curves. So that's just adding across the sun. But now I approximated the spectrum for deep water. This is essentially a spectrum you'd get from the one absorption spectra I could get if you stick a mirror 10 meters down in water, and so forth. And actually, it's very blue. I mean, the only colors you get are there. This little notch is blue. Otherwise, it's almost totally absorptive. But you'll see that little notch brings down the total amount absorbed by the blue planet to 214. And that's the ratio between those. So it's about 0.92 of the sun's energy is absorbed. 8% is reflected. And then applying the Stefan-Boltzmann fourth power relationship, that's a ratio of, in fourth powers, in energy, that's a ratio of 0.98. So you go and multiply that by what the temperature of just a flat, straight, what you calculated for this red curve, that's 279 degrees approximately. This is going to be 0.98 of that temperature, or 273. So actually, if we had a pure water planet, its equilibrium temperature would be just about freezing. But this is a crude approximation here. Now, this shows here, this straight line across here, the sun, or our reflectivity, average reflectivity of the Earth, as seen from the outside, with respect to the sun, is about 0.3. And I've multiplied these absorptivities by 10, so in terms of that, this is 0.7 here. This is the absorptivity that everybody sort of uses as a number compared to the sun's spectrum. Okay, we're absorbing 0.7% of the sun's energy according to them. And if we continue that all the way across so that it's just gray, this is the gray value, then we also assume it's 0.7 for in the infrared all the way across, the ratio is 1, we get this 279 degrees. Now the alarmists claim that while we reflect 0.3 here in the area of the spectrum where where we're emitting, we emit like a black body. We emit with 1.0. So going and looking at those computations, you've got 0.7 for the sun's area, or 1.0 for the infrared Earth temperature. Ratio is 0.7. Its fourth root is 0.915. And here's where you calculate this 255 degree Kelvin. If anybody has gone and looks around, sees anything on the global warming stuff, they will claim that we have a 33 centigrade greenhouse effect. They're taking from this. This is their null hypothesis, that we reflect 30% of the visible light essentially, but we reflect none. We're an absolute black body in the infrared, as opposed to using even a very crude approximation, like just consider, what would it be if we had the total spectrum of water? Okay, this point, water is like, well, it's 0.9 now. And actually, to go and explain the 288, just go and calculate backwards from the 288, and that would say that we actually have to be somewhat less reflective in the infrared than we are. But one of the things is, we're almost, well, okay, running along, okay. But everybody can go and ask me about the slides, and also look at them once we finish, just to get through this. Now here, actually, this is on a log scale, and this is from Wikipedia, actually, where the incoming light from the sun has been normalized to the same height, but it's essentially log scale on here, which you can see in the tick marks here. But this is the total absorptivity and scattering of the atmosphere. So the area, the light that gets to the ground is mainly in these parts where the things are here. So the temperature will be determined in those areas will be determined by the color of the ground, essentially. Now here, these are kind of squished compared to this. This is the contribution of water vapor to this. This is going to 100%. This is the black body level. Okay, 100%, absolute 1, and this is 0 in terms of absorption or emission. That's important to remember, that if something absorbs well, it also emits well. And these spectra multiply like stacking some filters. If half gets through the first filter, then half gets through the second filter, then a quarter gets through both. And you can see, when you compare this total absorption, now here's the absorption spectrum for water. Here's the absorption spectrum for CO2. Notice the only places where it has an effect on our color, as seen from space, are here in this interval here, and then you've got this peak here, which shows up here, and then this other one hardly makes any difference because water's already covering it's already opaque, essentially. So this is what in terms of spectrum, this is what the whole hysteria is about. And here's methane down here, and you can see that there's small contributions. But again, this harkens back to, one of the reasons why you don't have any runaways or anything is that, yes, CO2 absorbs very strongly, but just as well as it absorbs, it radiates to space. It just changes whether the radiation to space is coming from the surface or it's coming from the carbon dioxide up there. And in some ways, this extra law here, Beer-Lambert law, is essentially just this rule that filters stack, they multiply, implies a logarithmic, effect of having things. And here, this is about the level where that's necessary to sustain life. Okay, the first little bit of CO2 goes and makes a real big change in the spectrum. When we get out here, the difference between the level in 2010 and the doubling of pre-industrial level is just insignificant. What's that about? Whoop. Do I really want to?
Yes.
I guess, yeah. Music manager. Anyway, well, there's only one CO2 molecule for each 2,500 molecules of air. That's enough at the most absorptive frequencies to be virtually opaque within a couple of 100 meters of the ground. So, now we get to, here's the kicker, and I don't know whether this is Al Gore's witch doctor, James Hansen.
Once the planet gets warmer and warmer, then the oceans begin to evaporate, and water vapor is a very strong greenhouse gas.
I don't know that anybody can hear this.
Carbon dioxide. So you can get to a situation.
Essentially, yeah, you can go on the website
and
or go to the PowerPoint online.
So
get
hot
this.
that the ocean
But
the atmosphere, and that happened to Venus. That's why
he's essentially saying
no
that
has carbon.
Venus is Venus because it had this runaway greenhouse effect, and all the carbon dioxide went into the atmosphere, and it's got a very thick carbon dioxide atmosphere, and that is holding the heat in. But actually, by this very fundamental fact that it absorbs well, it also emits well. That just simply, well, to go ahead here to remind this, how incredibly hot Venus is. In fact, is here we go. Oh, should maybe move this one around. But one of the things is if you have a ball heated from the outside, and this is another one of those things, it's just as unbelievably. People go and talk about the Earth as if it was an incandescent light bulb with the heat source being on the inside. It's not. The heat source is out there. It's been heated from the outside. If you have an opaque ball, obviously, the atmosphere, the skinny little atmosphere, makes put a little shell on there, but fundamentally, if you have something like on Venus, the thing about Venus is you don't see Venus's surface from the outside. This is, actually, I don't believe this is a CO2 spectrum either. Venus, I think there's sulfites or something like that that are considered to be so incredibly reflective. It really is reflective. But one of the things is if all the heat is captured on the outside, then the divergence theorem says that any average on the inside has to be the same unless there are internal sources of heat, or sinks or sources of heat. This is the definition of divergence theorem, or intuitively from Wikipedia also. Anyway, so we get to these, what do we apply when we apply these computations to Venus? Venus is by far the most reflective of the inner planets. Its albedo is about 0.9. Its absorptivity is only about 0.1 as compared to the Earth's 0.7. So it's very reflective. Only a tenth of the sun's energy gets in the crucible. Its surface temperature is measured to be about 340 Kelvin. 740 Kelvin. Gray ball in its orbit, calculated like as above by Stefan Boltzmann, would be about 328. So a little bit over the boiling point of water. But its surface, because it's got this incredible, partly because it's got this incredible cloud layer, thick, very thick, is about 2¼ times the temperature of a gray ball in its orbit. Thus, the energy density at its surface, take that 2.5 to the fourth, and you get the energy density at the surface is 25.6 times the energy density in its orbit coming from the sun. So to explain this ratio of 2¼ in temperature, for this to be totally due to the energy absorbed from the sun, it must be 1/25 as absorptive in the infrared. And then it's 0.1 absorptivity in the visible. I mean, it has to be 25 times as reflective in the infrared as it is in the visible. That is, it has to have a reflectivity of about an absorptivity of about 0.004. And that's 10 times as reflective as the 99.96 of aluminum foil. So, ergo, Venus must have internal sources of heat. It cannot be explained as a runaway greenhouse effect. And if I could figure out a way to make a symmetric challenge, make a bet with somebody that they could not possibly go and construct any physical analog of Venus that showed anywhere nearly that ratio, I'd give them $10,000. And then just to go and show that we're. So that's it. James Hansen, Gore's witch doctor is just. I don't know how that. I do not understand how this got past a review committee. I mean, how in the. But